is Shaoshi Chen, currently at North Carolina State University, who got his PhD last year at Paris and Beijing, who will talk about proof of the Wilf-Zeilberger conjecture.
Thanks for the introduction. And today we're going to talk about the Wilf-Zeilberger conjecture. And this is joint work with Christopher Kuchen from RISC and Gus Painter, who was a former student of George Andrew. And now he's working in some companies. So first I give a very brief introduction to myself. And I got my master's degree from the Math Department of Chinese Academy of Sciences in Beijing. And then in 2007, I go to Paris for postdoc for my doctor. I participated in a doctor program between Beijing and Paris. So I stayed in Beijing for 6 months, then go to Paris for 6 months. Then I finished my PhD in 3 years. And then after my PhD, I go to RISC. I take a postdoc there for 6 months, working with many cars. And then now I'm working in North Carolina State University. So the year Wilf and Zeilberger proposed their conjecture is in 1992. At that time, I'm learning words by pictures, like apple and orange and banana and kiwis. And now the question is, what's the common name for those objects? So I think everyone knows the answer is fruit. So now let's jump to the high school or even college. So we learn many mathematics by teacher telling us some formulas like this: 1 over x plus, x or 1 over x plus n. We say this is a rational function, and x to the power n is power function, and the exponential function of like this. And many in the combinatorics we use a lot of factorials. And then I ask you, what's the common name for those functions? And if you have read this paper by Wilf and Zeilberger, you will know the answer is hypergeometric. Now, this talk is about this class of functions. Now, first let me outline my talk. First, I will give the definition of hypergeometric functions, which is a little bit different from the literature. And then I will describe a structure of this class of function. And then I will specify and give a formulation of Wilf-Zeilberger conjecture, which is roughly speaking, is something is proper, and if only if it's holonomic. Then I will give a proof and summarize my talk. First, by a hypergeometric function of several continuous variable t and several discrete variable x, we mean this function, if you take the Lagrange derivative of h with respect to the continuous variable and take this shift quotient with respect to discrete variables, they are all rational functions. Then we say this is a hypergeometric function. Here I denote di and sj be the derivations and the shifts respectively. So then I give some, in fact, why we are interested in this class of function, because you can represent this function by rational function, and then you can manipulate this function in computer. Now let's see some examples. Sure, because the rational function are hypergeometric. And the hyperexponential function means the hypergeometric function of only continuous variables. And then you will see that the usual exponential function are hypergeometric. And also some function to some irrational power is still hypergeometric. And the several kinds of symbolic power, which means symbolic power is here is a discrete variable, and the inside is a function of continuous variables. And then the usual hypergeometric terms are hypergeometric. So this is very typical examples. In the future, later I will show that you can build up any hypergeometric function by taking a product of those very basic functions.
So you mentioned that your definition of hypergeometric is slightly different from the one that we know from literature. What was the difference?
So the difference is usually we say the hypergeometric is you take so this is M1 like bivariate. So we say this after taking the generative function, we call this is a hypergeometric function. And then we say this is a hypergeometric term. But now I consider the something is you have you will not take the hypergeometric taking the generative function. So usual hypergeometric term is taking generative function of hypergeometric term. This is a little bit different. So let me, because the logarithm derivative of h and the shift quotient of h are rational function, I give the name of those rational function because they are certificates of h. And there is a correspondence between the function and its hypergeometric function and its certificates. For instance, if you take a product of two hypergeometric functions, which corresponds to taking the sum of the certificates with respect to the continuous variable, and with respect to the discrete variable, you take the product. So this is the correspondence. And for example, if you have this product, and then you can calculate the certificate of this function. So this corresponds to here. So usually with respect to the continuous variable is the additive, and with the discrete variable is the multiplicative. So here is corresponding to here, and the black one corresponds here and go to here. So you can see this is a one-to-one correspondence between the function and its certificate. So you can easily calculate the certificate of a hypergeometric function by this correspondence. Note that x factor. So they are if this is free of discrete variable, then this has no contribution to the certificate with respect to discrete variable. So now you see the certificates almost describe the property of a hypergeometric function itself. Now I would, because the certificates come from just one hypergeometric function. They are not arbitrary rational function. They satisfy the following we call the compatibility conditions. So let me first give a definition. Actually, a rational function a1 to am, b1 to bn are said to be compatible if they satisfy the following three groups of conditions. And the meaning of those compatibility conditions is, say, those rational functions satisfy this system of linear differential equation. Note that they are not linear. In fact, they are nonlinear. And then you can observe that certificates of hypergeometric function are compatible. So let me show you one example how does this compatibility condition come from. So just to show you one example. For instance, you have this bivariate hypergeometric function. T is continuous variable, x is discrete variable, and then if I denote this is A, and Sx, this is B, then I will show you how to derive the compatibility condition. Note that because usually I will assume that this is true. So then you calculate this side. So you have dt, so Sx is equal to Bh, and then you use the Leibniz rule, you get dtB h plus, and then you have dth. Now you get dtb plus ab times h. And then from this side you can calculate sh and ah. So you get axa, sh, h. And then you get sa times b times h. Because they are equal, and I usually assume that h is non-zero, then you get and you move this to here, and then you get So this is exactly the one of the compatibility contained here. You can also derive this from this and this. So this is the compatibility condition for certificates. And then to exploit the structure of hypergeometric function, so the first step is we would like to exploit to describe the general solution of this linear differential system. So this is the structure theorem. So if A1 to AM, B1 to Bn satisfy this satisfy compatibility condition as previous slides, and then we can get additive decomposition of the certificate with respect to continuous variable, and the multiplicative decomposition of the certificate with respect to discrete variable. So basically, so this result is the meaning of this result. You can translate this structure to the function level. So if this as a corollary, we can show that any hypergeometric function is conjugate to the following form. So let's make a remark. Here the red part will go to the rational here. And then this the blue part will go to this symbolic power functions. And then this is goes to the black part, and this is brown is going to here. This is, you can translate this by the correspondence between the certificate and the hypergeometric functions. And why I say conjugate, the meaning of conjugate is the function h and this function, they have the same certificate. So maybe there are two functions, they have the same certificate, but the representation maybe is different. But this is mean that they both, you can take this as a representation of h. And then, the remark here is f is a rational function. So now you can see that any hypergeometric function can be written as the product of some value via familiar functions like rational function, power function, exponential function, and factorials. So they are all a very basic function. So now I can give the definition of what the meaning of the properness. So a hyperexponential function h is said to be proper, which means if it's conjugate to a function of the following form. You can forget this form. The only thing is difference. The proper one, difference from the non-proper one is the rational part. So now the rational part is a polynomial. Then we call it proper. Just to remind you, anyone is just here rational, and then proper one is the difference here is polynomial. Then we call this proper. And then we can show that any rational function, if a rational function is proper, we can give a very explicit form of this rational function. The only the significant thing is the denominator is of this special form. Here, the continuous variable and the discrete variable are separated, and the polynomial of discrete variables are product of some we call the integer linear. Why integer linear? Because here the coefficient vi are integers, an integer vector, and the lambda I you can take any element in the ground field. And then there is a very nice algorithm. We can check whether a given hyperexponential function is proper or not. So basically, we can decide any hyperexponential function. Usually, how you can define the hyperexponential is to give the certificate of this. We can take the certificate as input and decide whether this hypergeometric function is proper or not. So this is the key lemma to verify the properness. Now we know what's meaning of the properness. Now let's go to...
Is it that the certificates that you input have to satisfy to make it proper?
Yes. So the idea is you first compute this this decomposition of the certificate. Then you can translate it to the function form. And then you check the rational part.
Okay.
And then you use this lemma.
Yes,
the denominator is of this special form, then you can say this proper. This is the argument.
Is that the same thing that you did in the program?
No, this is new. This is new result, sorry. This is new result. This is my new result. Thank you. So we are nice. We are happy because now we can do something algorithmically. So now let's go to the...
very powerful extension.
Okay, now let's go to a more technical part. This is the most technical slide in this talk. So we call now we give the definition of the holonomicity. So a function, any function of continuous variable is said to be holonomic. So let me first give some notation. So here this one is the denote AS sub S denotes the S Y algebra. So the Y algebra essentially is this is a polynomial and this is an operator. They satisfy some special rule of some special multiplication rule. And then with this algebra, you can take some module of this algebra. Then you can define the module is something like you can act this algebra to some ring of functions. Then given any function, you can define the annihilating idea of this function. So this is just you select some you collect some operator which annihilates vanish at this function. So this is you can check that this is the idea of this in this ring. Now what's the meaning of holonomic is you have this annihilating ideal. Theoretically, you can compute the Hilbert dimension. And then you can say if the Hilbert dimension is just this S, then we call this function is holonomic. There is a very strong inequality about the Hilbert dimension of this annihilating ideal. It says the dimension, Hilbert dimension of any left ideal is greater than S. So this is any left ideal of AS. So in particular, annihilating ideal is the left ideal of this. So we know already, a priori we know the dimension is greater or equal to than S. So the holonomic means this when this dimension is minimum, then this is holonomic, the minimum. Or this is the Bernstein's inequality. So this is, in some sense, holonomic means something is minimum. And then so here the definition is just for function of continuous variable. Now let's give a definition of holonomicity of function of several continuous variable and several discrete variable. The ingredient is to take the generating function of this function with respect to, you will introduce several continuous variables z1 to zn. Now you get a function of purely continuous variables. Then you can apply this definition, say this is a holonomic, if only if this is holonomic over this Y algebra. Now you have m plus n operator. And this is very, is very theoretical definition of holonomicity. And for the moment, for any given function, there are no argument to verify this property. So, but amazingly, in this, so you will see in this paper by Wilf and Zeilberger in 1992, and this is also very fundamental paper of the, now we call the Wilf-Zeilberger's method. And this this is also very, people cited this paper several 277 times. So it's very famous paper. And then in this paper, what I think the most important sentence is this one. So they say our examples are all proper hypergeometric. We conject that a hypergeometric function hypergeometric term is proper. Here, I replace this by function because term is for discrete case. So. Yeah. And is proper hypergeometric if and only if is holonomic. So what's the real meaning of this sentence is this is a bridge between the holonomic properness and the holonomicity. Now we know that we know how to verify the properness, but theoretically there are no argument to verify this holonomicity. So if this conjecture is true, now we can claim that we have argument to decide whether a given function is holonomic or not. So this is why this main motivation why we want to prove this conjecture. So now let me give a review of previous work. So in the continuous case, this conjecture can be verified easily. So there are some results by Bernstein and Kashiwara. The main result of Kashiwara is say in the continuous setting to verify a function is holonomic or not is equivalent to verify this function is definite or not. What's the meaning of definite? If you take the all kinds of derivatives, then you generate this derivative over the rational function field. If this is a vector space, if this vector space is finitely dimensional over the rational function field, then we call the function is definite. And usually, it's easier to verify a function is definite or not. And then Kaspar's results say holonomic and definite in the continuous sense are equivalent. So this is very remarkable result. And also Takayama gave a very elementary proof this very deep result. And this result is also published in this invention mathematics. And there is some result by Christopher in 1999. He gives some structural result about the bivariate hypergeometric function of continuous variable. And then with this structural result, you can verify this conjecture.
What was the elementary idea of Takayama in proving
so in this paper, they use a lot of D-module and the very heavy machining to prove this result. And then Takayama give a very elementary proof.
Without using modules?
No, without using module, and usual people can read this paper. But for very non-usual people can read this. So maybe for algebra is easy. And then let's go to the discrete case. So discrete is very hard, but it's solved. So the first time is solved by a student of named Gus Pena. He was a student of George Andrew. He did his PhD thesis in the discrete case of Wilf-Zeilberger conjecture. And this is in 1997. And it's because he only published this result in his thesis. There are no journal, and then there are several people rediscovered the way to prove this this conjecture. And one of the important is by one of is Abramov and Peter Kovshek. Actually, the results are independent, so there are no conflicts. And then, but the original conjecture is about the mixed case. So, in the discrete case, we need one very key result is called the Ore-Sato's theorem, which describes the structure of multivariate hypergeometric term. So with this structure theorem, we can prove the conjecture. So the natural question is whether we can have a structure theorem for in the mixed case. But I have already showed this before. Now let me start the idea of how to prove this result. So the holonomicity will be preserved under some very basic operations. For instance, if H1 and H2 are holonomic, and then the sum and the product of H1, H2 are both holonomic. So you can, I will not show this, but this is true. And then we can, so to prove the conjecture, you have two steps, because the conjecture say properness is equivalent to holonomic. Now this slide will show you if it's proper, this implies holonomic. So but we know that any proper hypergeometric function is product of the following four basic functions. Now let's check all those basic functions. So we can prove that all those hypergeometric special functions are holonomic. So basically, you can easily to check that polynomial is holonomic, and the usual this is the exponential function of purely a continuous variable, and then by Kasparov equivalence, you can easily check this is holonomic. And then the power function, you can calculate this geometric function. You can get you can show that this is if you take the geometric function of this one, you can even show that the geometric function is rational. Then by Kasparov's result, you can show that this is also holonomic. And then for factorials, then I use the proof in the discrete case, because in discrete you need to verify that all factorials are holonomic. So I don't need to redo everything. And then by this proposition, and then you can show that properness implies holonomic. So this step is much easier than the next one. Then it remains to show that holonomic implies properness. And then you should explore more property about the holonomic ideas. So this is the main property of holonomic ideas. So the lemma says if H is a holonomic function over rational function field, then for any, you can select any discrete variable. No, you can select any index with respect to the continuous variable and any index with respect to the discrete variable. Then, if this is holonomic, then you can show that there exists non-zero operator of this special form. So the basic information of this operator is you can see that if you count the number of variables, this is the m plus n minus 1. And then here plus 2, you have how many variables in general is m plus n plus 1, many variables. And then the holonomic means the dimension, Hilbert dimension is, in this case, is m plus n. So you can guarantee that there exists this elimination property for this. But in this case, in this mixed setting, the proof of this elimination property is not so straightforward because because you take the generative function. So there's something is not so easy. So this is the property of elimination property. Now, to prove that any holonomic function h, hypergeometric function h, is proper, then you should reduce. Now we will try to reduce the conjecture to the rational case. So the main observation is if this is the general form of any hypergeometric function, and then one can check that this part is holonomic and its inverse is still holonomic. So this is the observation. And then by the closure property, because you can always multiply, because this is holonomic, if you multiply this, you will cancel this part. Then the only remain is a rational part. So then you can get if H is holonomic, then if and only if the rational part is holonomic. So this is by closure property. Okay. Now in order to prove the conjecture, we will focus on the rational functions. So then this lemma will tell you, so if f is a rational function and f is also holonomic, then we can prove that f is of this special form. And this coincides with the properness of the rational function. So then you can prove that, so this also implies that holonomic implies properness. So this is the idea. And to prove this, the special form of special form of holonomic rational function, we need this elimination property. So the first you will use elimination property to prove that the denominator, the continuous variable and the discrete variable are separate. You will use the elimination property, and then you apply the method which used in the discrete to say here is integer linear. So we will also use some result in the discrete case. Then we combine together, then we get the general proof. Now let me give a. Now we have proved this conjecture, and then with this conjecture we can show some example which is very elementary, but it's not a holonomic. For instance, this example. So here n and k are both discrete, and then this is a rational function, and then by this previous result here should be integer linear, and then you can prove that you cannot factor this into a two-factor with the coefficient integer linear. So this is not a holonomic. And here more interesting is this very simple rational function. X is here x is continuous variable, n is discrete variable, and then you can show that x plus n cannot be fact. You cannot write x plus n like bx and like c. You cannot separate this variable. You cannot write this.
You can't write it as a product, right?
No, you cannot write it as a product.
Product of continuous.
Yes, yeah. This is, and then this is not holonomic. So this is very actually this conjecture. Before we proving this is not so easy to check this is holonomic or not. So now we know this is not a problem. So
no, but indirectly, no, because the sum of n